So, in today's lecture, we are going to be talking about standard atmosphere. So, in standard atmosphere, what we are going to be seeing is what happens to certain values or functions as we go higher. So, that means from the ground, okay, if I keep going higher, that is, if my altitude is increasing, what will happen to pressure, density, and temperature? So, what I'm going to do is, as function of altitude, we need three things. We need what is the pressure, which is in pascals. We need the air density, which is in kg per meter cube. And we also need temperature, is T, which is measured in Kelvin. So, what I'm trying to say is that if you keep going higher and higher, how will the pressure change? How will the air density change? And how will the temperature change? So, that is what we need. That is the whole purpose of studying this topic called standard atmosphere. Now, what you have to remember is that this standard atmosphere is physically correct. What does this mean? It means that it obeys the equation of state. What is the meaning of that? What is the equation of state? The equation of state is P is equal to rho RT. So a standard atmosphere will obey this equation of state. So what is R equal to 287.00 joule per kg Kelvin. And the pressure increase due to gravity. Now, what does this mean? We'll look at this in some time. So remember that what are we trying to achieve? Where we are going to try to find a function for pressure, density, and temperature as we go higher. That is something you have to remember. In the last lecture, I had derived what is the hydrostatic equation. We derived this in the last lecture. The hydrostatic equation is dP is equal to minus rho g dH. So here you can see something over here. It means that you can see there is a negative sign also over here. If the height is increasing, then the pressure as we go up should decrease. That is what this hydrostatic equation says, which is correct. As you go higher and higher in the atmosphere, we know that the pressure actually decreases. And that is given by this equation, dP is equal to minus rho g dH. Till now, we have seen two equations. What are the two equations? That it obeys P is equal to rho RT. And the other equation is the hydrostatic equation, that is dP is equal to minus rho g dH. And first, we will start with defining what is the value for pressure. But before we do that, I want to show you a graph, okay, very interesting graph that you should remember. And I'm going to just put that graph over here. It's called as the International Standard Atmosphere Temperature Profile. So this is called as the ISA, the Standard Atmosphere, International Standard Atmosphere Temperature Profile. Okay. Let's see what do you mean by this. Now, if you notice, and there are some values that you have to remember. At sea level, the height is 0 meters. At sea level, the International Standard Atmosphere says that the pressure at sea level is to be taken as 101,325 pascals. It is decided by we take this as the standard. And the temperature is 15 degrees Celsius, which is equal to 288.15 Kelvin. And the density is 1.225 kg per meter cube. This is the starting value. So where is that point? That point you see is over here at this point where the height is 0. Until a certain height, if you notice here, the troposphere is up till 11 kilometers. What is this red line that you're seeing over here? The red line is basically showing that if it is traveling towards the left, you can see the red line is going towards the left, which means as I go higher, you can see that the temperature is reducing. And if the height is increasing. Okay, so we are going higher. So that means in the troposphere, as we go up, there is a reduction in temperature. And then from 11 kilometers to 20 kilometers, you can see it is the temperature remains constant. Then in the stratosphere, you can see that the temperature goes on increasing, and then again it becomes constant, then it reduces, and then again it becomes constant, and then again it increases. For our course, we are not going to go beyond 30 to 35 kilometers. Okay, so you should know that there is a region where the temperature reduces, that is troposphere, and in this region the temperature is constant, that is the tropopause, and after that the temperature increases in the stratosphere as you go higher. Now this is something that you all have to remember. Now there is something that you need to know, and I'm going to show you so we'll talk about the level name and what is the height, the base height. You have to take this table down, it's very important. And we'll look at what is the base temperature, and we will take this temperature in degrees Celsius. And then we have something called as the lapse rate, which is degrees Celsius per kilometer. And then we will see what is the base atmospheric pressure. So the level name first we will talk about is troposphere. In the troposphere, the base height is 0, and this is in kilometers. The base temperature according to standard atmosphere, I know the base temperature is 15 degrees Celsius. What is the lapse rate? It is minus 6.5. And the base atmospheric pressure is 101325 pascals. Now we'll go to the next part, which is tropopause. The base height is 11,000. It's only 11. Okay, it's 11 kilometers. And the lapse rate is 0. Okay, next is stratosphere. Stratosphere is 20 kilometers, and this is plus 1.0. And we'll stop with this only. And I want you to pay attention to this. The next level is 32, and that is also the second stratosphere 2 I will write. So that is 32, and from 20 to 32 kilometers, the lapse rate is 2.8. Now let's understand what this means. I'm not putting the values over here because these values we are going to be calculating later on. We will do an exercise and we will calculate these values. Now, what is the meaning of minus 6.5 degrees per kilometer? The meaning is that if this is the ground, if I'm at 0 kilometers, and if the temperature is 15 degrees Celsius, if I go up by a height of 1 kilometer, then what should happen to my... So if you go by a height of 1 kilometer, you can see that for every kilometer, the temperature reduces by 6.5 degrees. So the temperature will actually become 8.5 degrees Celsius after 1 kilometer. Similarly, if you go higher by another kilometer, then what will be the temperature? The temperature will become less by 6.5, so it becomes 1 degree Celsius. So as you can see that for every kilometer, the value of temperature is reducing by 6.5 degrees Celsius. However, instead of doing that, my suggestion is that the lapse rate is usually written as A. Take the value of A in terms of meters. So this is 6.5 kilometers as degrees per kilometer. You can use minus 6.5 for every, let's convert this into by 1000, and this will become minus 0.0065 degree per meter. So we will use this instead of minus 6.5. I just want you all to calculate what do you think will be the temperature at 11 kilometers height. It's very simple. You have to use this and get me the temperature at 11 kilometers. This is minus 56.5 degrees Celsius. Now you can see that in the tropopause and stratosphere, from 11 to 20 kilometers, the lapse rate is 0. That means my temperature does not change at all. So my temperature at 20 kilometers also will be minus 56.5 degrees Celsius. So these are some values you have to remember. I'm going to leave it to you to get the value for this box. Okay, you can do this as an exercise. Remember that the lapse rate over here is 1 degree per kilometer. So from 20 to 32, there is 12 kilometers. So the temperature will rise by 12 degrees. Okay, so I'll give you a formula. To calculate this, you have to use something called as Toussaint's formula. This is how you will calculate the temperature at any height. And what is the temperature? The formula is T1 is equal to T naught plus A into H1 minus H naught. A is nothing but the lapse rate. I'll explain everything. So take this as your base temperature, and this is the temperature at height which you want. This is the base height. So in our case, I wanted to calculate what is the temperature at 11 kilometers. So my base height was 0 and I wanted to calculate at 11. So what should I do? So I need to calculate what is the temperature at 11 kilometers, which is equal to temperature at 0 kilometers minus 0.0065 into height. The height of the level is 11,000 meters minus the base height, which is 0. So here you will, I know this value is 200 and what is the value that we have? It is in 15 degrees. So this is minus 0.0065 into 11,000. So if I do this, you should get you will get minus 56.5. Now in the next topic, what we are going to do is, so we have found out, so I'll write it over here. We now know how to calculate temperature with respect to height. When I started the course, when I started the lecture today, what did I say? As a function of altitude, we need to know how pressure changes, how density changes, and how temperature changes. So we have already done this. Now we have to do for pressure and we have to do density also. So we still haven't done pressure and air density. So now we'll go to see how pressure changes with altitude. So that is the next part. So we have all seen that the pressure changes with respect to altitude is minus rho g dh. We have seen that. This is how the pressure is going to change. Okay. There is a problem with this formula. The problem is that as the altitude increases, the density also changes. The air becomes thinner as we go higher. That's why when you are climbing mountains, after a height of 15,000, 16,000 feet, you will not be able to breathe properly because the air is becoming thin, the oxygen content will go down. So density is also changing. Height is also changing, density is also changing. So there is a problem. Gravity we have kept constant. So now what should I do? I should get rid of density. I don't want density. So how will I remove density? I can remove density by writing P. I know P is equal to rho RT. So density is equal to P divided by RT. So I will use this density and I will substitute it back in equation number 1. So this is 2. So what I'll do is substitute 2 in 1. So what do I get? I will get dP is equal to minus P by RT into G dH. Please remember, what are we trying to do? We are trying to see how pressure is changing with altitude. Okay. But because the density term is there, I want to remove density and leave and replace it with pressure and temperature. Now you will ask, now people will say, sir, but temperature is also changing. Correct. The temperature is also changing. Now we saw what is the lapse rate. A is called as the lapse rate. And what is lapse rate? It is given in degrees per kilometer, which can be written as the change in temperature divided by the change in height. That is lapse rate. Or I can say that dH is equal to dt by A. So I can replace dH with dt by A. So now what we are going to do is, and let me call this as 3. So what should I do for 3? I will put 3 into this equation. So now this will become, and I will take P to the other side. So dP divided by P is equal to minus G by R, and dH can be written as, or there is a T over here, and dH is dt upon A. I'm coming very close to what I want. I'm going to integrate here, and I'm going to integrate on the right hand side also. We are integrating with respect to P and integrating dt over here. Now we know that, so that means I'm going to go from the pressure P naught to some pressure P1 and the temperature T naught to some temperature T1. What does this mean? That means if I am at some base level, I know the pressure is P naught. But if I go to a certain height, then what will my pressure become? It will become P1. And I know the temperature is T naught and the temperature is T1. This is what I'm trying to do. I'm trying to calculate what is the change in. Okay, now, how do I do this? I know that integration of dx by x is equal to natural log of x. So what will this become? This will become natural log of p from p naught to p naught p1. Similarly, g is a constant, r is a constant, a is a constant, and integration of dt by t is nothing but natural log of t from t1 to t2. So now I have to substitute the upper limit. So that is natural log of p1 minus natural log of p naught should be equal to t1, t naught and t1. Okay, this is fine. So minus g by ar, natural log of t1 to natural log of t naught. We know that natural log of a minus natural log of b can be written as natural log of a by b. So similarly, I can rewrite this as natural log of p1 by p naught is equal to minus g by ar natural log of t1 by t naught. Now, we also know that if you write, let's say, a natural log of x, so this a can come over here as the power of x. So this can also be written as natural log of x to the power of a. So similarly, here also I can see that natural log of p1 by p naught is equal to natural log of t1 by t naught to the power of minus g by ar. And now you can see natural log is there on both sides. So p1 divided by p naught is equal to t1 by t naught to the power of minus g by ar. This is the formula to calculate the pressure between any two heights. This is the formula to calculate the pressure between any two heights. Okay, so I have now calculated using this formula. I know how pressure changes with altitude. But now I need to calculate density, how density also changes. Now we need to calculate the density. I know that pressure is equal to rho RT. So that means in the place of P1, I can replace rho 1 R T1, and in the place of P naught, I'll replace rho naught R T naught. And this will be equal to T1 by T naught to the power of minus G by AR. And now you can see R and R cancels. You have rho 1 by rho naught. And this T1 by T naught to the power of 1, when it goes to the other side, what will happen? It will become minus 1. So it will become T1 by T naught minus G by AR minus 1. So this is the formula for calculating the change in density between any two heights. Very important. So I'm going to rewrite these two equations so that you can copy this down. Now see, there is a problem with these two equations. When can you use this equation and when you should not use this equation? You can use it in the troposphere where the value of A is minus 0.0065 degrees per meter. But you cannot use this formula in this region, in the tropopause. Why? Because in tropopause, the lapse rate is 0. you can see the temperature does not change in the tropopause. So from 11 kilometers to 20 kilometers, you cannot use this formula because in this region, the temperature is constant. Or I can also show you something here. If you try to use this formula anywhere else, so let's say if you use it in tropopause, where the value of A is equal to 0, what will happen? If you substitute 0 over here, anything divided by 0 becomes infinite, or rather, it becomes undefined. So you cannot use this in tropopause. So what should I do in tropopause? How do I use, what formula will I use when A is equal to 0? So when A is equal to 0, then let's go back and see the same formula where we started deriving from. When temperature is constant, I know that dP by P is equal to minus G by RT times dH. Now, you see, in this case, the temperature is constant, gravity is constant, and R, the acceleration due to gravity and the value of R, all are constant. So I don't need to do anything. All I need to do is integrate from these two sides, from P naught to P1 and from H naught to H1. That's all I need to do. In this case, I only need the change in height. So what will this become? This will become natural log of P, P1 by P naught is equal to minus G by RT. Integration of dx is simply x. So here integration of dh will be h from h1 minus h naught. That is the integration. So now P1 by P naught. If I take natural log to the other side, so for example, if I have natural log of x is equal to a, if natural log goes to the other side, then it will become e to the power of a. So similarly, this will become e to the power of minus g by rt into h1 minus h naught. So this is the formula for the change in pressure when the temperature is constant. So now we have P1 by P naught, but density will become rho 1 by rho naught. How did I do this? Because in the place of P1, I am substituting rho 1 RT1 and here rho naught RT naught. But I know T1 and T naught is constant in when temperature is constant, T naught, T1 will be the same, R and R will be the same. So rho 1 by rho naught is also the same formula, e to the power of minus G by RT H1 minus H naught. This is also the same. Now we'll do very interesting problem. Now I'll speak about a specific person, and this guy set the world record, and I'll show you something. Wait. So we'll see Joe Kittiger. His name is Joe Kittiger. He was a United States air officer, and you see this picture over here. You can see he is taking a jump from very high in space. Okay, he was actually a record jump. He is basically trying to jump from a very high aircraft. It was actually a balloon. It went very high, and he jumped from there, and he set the record. And this was in 1960. So he jumped from a height of. So this is Joe Kittiger. So what did he do? He took a jump from a height of 31,333 meters, about 31 kilometers above the earth. From there, he took a jump. So let's see. This is a very interesting problem that we are going to do. So first we will start from the base where the height h naught, let me call this as h naught. And then there is a troposphere, which is at a height of h1. Let me call this as 11 kilometers. And then you have the second layer, which I'm talking about, that is h2, which is a height of 20 kilometers. And in the first region, A is minus 0.0065 Kelvin per meter. Now, whether you take degree per meter or Kelvin per meter, it does not change. It's the same. So we'll take Kelvin per meter now. A is equal to 0 in this range from 11 to 20. The next height I told you was at 32 kilometers. But where is he jumping from? He jumped from 31,333. So he's jumping slightly below that height. And let me call that height as H3. What we are going to do in this problem is we are going to calculate what is the pressure P3 at this height, what is the temperature T3 at this height, and what is the density rho 3 at this height. We will calculate all three. And where are we starting from? We are starting from P naught and T naught and rho naught. And these values we already have. So P naught is equal to 101,325 pascals. T naught is equal to 288.15 Kelvin, because that is 15 degrees Celsius. And the density is 1.225 kilogram per meter cube. But before we go to straight away to P3, T3 and rho 3, we cannot go straight away like this. First step is we need to calculate what is the temperature at, what is P1, what is T1, and what is rho 1. We have already calculated what is the temperature T1 at 11 kilometers height at the starting of this. So 216.5 Kelvin was the value which we calculated. But now we need to calculate what is P1 and what is rho 1. What formula can I use to calculate P1 and rho 1? I can use the formula which we derived when the value of A is not constant. I told you we can use this formula in the troposphere. I can use this. So in order to calculate P1 and rho 1, I'll use these two formula. So now you know what is P1. I mean, P1 is what you have to calculate. So this is a question mark. P naught you have, T1 you have, T naught you have, G you know, A you know, and R you know. If you know everything, all you have to do is calculate P1 at 11 kilometers height. What will be the value of pressure? Even more accurate value of G would be 9.80665 meter per second square. But if you've taken 9.81, it's fine. Or everyone, let's take 9.81 only. Okay, let's take 9.81. 22388 pascals. So at 11 kilometers height, can you see that originally it was 101,000 and now it is 22,000. So it is reduced by 1/5. The pressure is reduced by 1/5. Okay, now what is the density at that height? A is minus 0.0065 Kelvin per meter. In order to calculate density, do not use this formula. You can use this also to get, but you see, instead of rho 1, I can simply write P1 by RT1. I can use this formula also. You calculated P1, you have T1, and you know R. This will give you the answer 0.359 kg per meter cube. All right. So now that you've got this, now we will go to the next level. The next level is H2. So now we will have to calculate what is P2, what is my T2, and what is my rho 2. Now there's one interesting thing. Here the lapse rate is 0. So that means the temperature is not changing. So whatever is your T1 will be your T2. So T2 is also 216.5 Kelvin. And we also know what is the formula that we need to use when the lapse rate is not, there is no lapse rate. Okay, if it is 0, you will use this formula to calculate the value of P2. So you can write P2 divided by P1 is equal to e to the power of minus G by R T. Whether you write T1, T2 doesn't matter. And the height is H2 minus H1. P1 I already know. G I know. R I know. T I know. H2 and H1 also I know. H2 is at a height of 20 kilometers, so 20,000 meters. H1 is a height of 11,000. So you can see the pressure has become 5406.48 Pascal. The next thing you have to calculate is what is the density rho 2. How will you do this? Just use P2 divided by R or RT, whatever. 0.087. You see, this is really, really small. It almost says that there is density is almost 0. That's why after 20 kilometers, it's almost impossible to breathe. And that's why you can see when he was jumping from the space suit, he had to jump with an oxygen cylinder. You can't jump simply like that, you'll die. And the temperature, you can see it is very cold, minus 56.5. He will instantly freeze. That's why he's wearing a space suit also. So you can't just jump like that. You'll have to jump with cylinder. So we have calculated what is P2, we have calculated T2, and we have calculated rho 2. All three done. Now in the next segment again, you can see that the value of A, the lapse rate is given to you as plus 1, or rather plus 0.001 Kelvin per meter. This you have to do. And what is the height? It is 31,333 meters. So what formula will you use again? You will use the lapse, the formula which also includes the lapse rate. So we know P2, and now we have to calculate what is T3. How do I calculate T3? I will use the Toussaint formula. Again, the Toussaint formula to calculate T3. This is very simple. So you can see this is the formula. So T3 is equal to T2 plus A times 31,333 minus 20,000. And A is given to you as 0.001 Kelvin per meter. T2 you already have, which is 216.5 Kelvin. So 228.5 Kelvin. Okay, so T3 you have. Now P2 you have, P2 we just calculated, it is 5406.98 pascals. So use that formula which we have derived with lapse rate and give me the answer. The lapse rate formula is here. We've derived this. Just the pressure one you will need. You can get the answer. So if I do this, it is P3 divided by P2 is equal to T3 divided by T2 to the power of minus G by AR. What is P3? Pressure also approximately becomes absolutely zero. You can see it's very close to no pressure at all at that height. So that's why you have to wear a space suit, because if there is no pressure, your body will explode. So in order to be in such low pressure, you have to wear a space suit, and it is pressurized. So you can't jump just like that. Okay, so P3 is 864 Pascal. And what is
Density
T3?
is
Density, rho 3?
0.013 kg per meter square. Meter
Rho
cube.
3 into, so this is the density. All right. So I think everybody got this so far. So there is chapter number 3 in the textbook that he has done. We have studied that chapter. Chapter number 3, it's called the standard atmosphere. You can try to do problems from there, from the last problems at page number 132. You will find the problems in that textbook. Try to do it on your own, and I will also share a worksheet with you all that you can practice. All right, we are done with today's lecture. We'll meet again tomorrow.